Go.
Okay, so this talk will be on algorithms rule supreme. This is a repeat of a talk that I gave at the Embedded Systems Conference back in October in the Bay Area. So I'm Lloyd Moore. I've been doing embedded systems engineering for about 30 years, various capacities. Embedded, Linux, machine vision, robotics, all that type of stuff. Everybody in here pretty much knows me, but that's mostly for the people on the tape. Code optimizations can get you 2 to 4x improvement. Changing your algorithm can get you more than 10x improvement. Okay, so matching, what we're going to talk about tonight is primarily matching your algorithm design to your workload. We're going to look at basically how to do that, and we're going to take a look at 3 different approaches. So all of these have to do with what's called connectivity analysis. How many people in here have any machine vision background? None. Okay, I'll go into a little more depth on what that is. So first thing we'll do is define what connectivity or blob analysis is. Then we're going to look at a traditional approach, an approach I call the wanderer approach, and an approach I'm going to call the single pass approach. And we're going to compare and summarize each one of these. So what is connectivity analysis? As I mentioned, it's also called blob analysis. If you have an image, and you look at that image from the computer's perspective, it's a bunch of pixels. They're all individual. If you look at it as a human, essentially, if I hold up this piece of paper, and I look at this with a camera, it's a bunch of pixels. They're all disconnected. If I look at this, I recognize all those pixels or those spots as a single unit. Okay? They're all connected. The way you tell how they're connected is pixels of the same general color are touching each other. That's the first level of analysis. That's what's called connectivity analysis. What pixel is connected to what? You do that by figuring out which pixels are adjacent. For this discussion, we're going to use a monochrome image. So this simplifies it considerably. So if 2 pixels are touching, they are part of the same thing. Yes?
You brought up an interesting point. Making it monochrome simplifies the problem.
Mm-hmm.
So if you're like creating a license plate reader, wouldn't it be much easier to just take a black and white image and deal with it than a color?
That's actually what they do.
It is?
It's exactly what they do. So if you do full-on machine vision, and let me even take it one step further, your brain actually does this as well. Even though you perceive things in color, the image processing algorithm for both machines and humans, and we assume most other mammals, strips away the color information, leaves you with a monochrome or black and white image, and then performs the first level of analysis on that black and white image. When that analysis is done, the color information, if it's necessary, is overlaid back on top of it. Now, if you really want a beautiful example of this, and I wish I still had it, just to give you an example of how your mind can play games with you. How many people remember the overhead projectors? Okay? How many people remember there was a box that sits here and it had an arm and it projected up and you put slide transparencies on it? Yep.
Oh, yeah.
When they first came out, before they had fancy projectors like this, you took an LCD panel and you put that on top of the overhead projector. And that's how you presented computer information. I was in college at the time and working in the computer lab. The color ones were not that great. Okay, they didn't have the full TFT color LCDs like they have now. But what I did, I was away for the summer and I came in. They'd gotten a nice high-res black and white monochrome overlay on top for the projector. And it was set up much like this. You had the projector here and you had a monitor here. I was working on this thing. I looked at the monitor, and then I looked up at the screen. And I did this several times while I was working on it. I perceived the screen in color. Because your brain overlays color information. It recognized that's the same image and overlaid it. And there's several visual illusions you can play like that will overlay color information on top of what should be a black and white image, or vice versa. I had a pair of sunglasses and an umbrella, but the filters on the sunglasses perfectly canceled out the yellow on the black and yellow umbrella. And I used to, I was in psychology at the time, I used to play a little trick on people. Have them put the sunglasses on, right? I just show them the umbrella. What color is the umbrella? Black and white. Take the sunglasses off. What color is the umbrella? Yellow and black. Put the sunglasses back on. What color is the umbrella? Yellow and black. Because your brain remembered the color and remapped it onto the image that you were seeing. So, little psychology side tour there. Anyway, back to blob analysis. So you basically start off with everything in black and white. And if a pixel is touching, the first level is you make that connection. So for our discussion, we're going to put all these things together, and we're going to represent an object by a bounding box. So when we figure out what this is, we're just going to simply draw a box around it and call everything in that box one object. And you'll find that works just fine for the types of problems we're going to talk about. Okay, we're going to compare the algorithms. We're going to be doing this by counting operations in pseudocode. Just to keep things simple, we're going to call the pixels, or the images, 100 by 100 pixels in size. Just keeps the math a little simple and something you can kind of, do in your head pretty straightforward. The algorithms are a bit simplified for the presentation, although not too bad. We're also going to consider the memory and cache friendliness separate from the operations. Okay, so there's different impacts on the memory usage pattern. And then we're going to consider the advantages and disadvantages for the image content itself. And again, the three algorithms we're going to talk about. So, first algorithm, I'm going to call the traditional algorithm. This is basically a textbook approach. If you pick up a book on machine vision, and they're telling you, connectivity analysis, this is the algorithm they're going to show you, or a slight variant of it. It doesn't make any assumptions about the blobs in an image. Okay, so they don't make any assumption about what the image is. This is going to serve as a baseline for the other algorithms. And I'm going to make a note, you probably don't want to do this in real life. As you're going to see, performance isn't super great, but it's common. People do use it, and it serves as a good starting point. So here's how this works. All these comparisons are going to follow the same pattern, where on top, as we start out, I'm going to have a kind of a graphic representation of how the image processing progresses, and a description of the steps. So on the left-hand side is just the raw image. And I just drew these gray. They actually could be different shades of gray. Okay? But you have black and gray at some level. The first thing to do is to apply what's called a threshold operation. So this forces the image to be black or white. Basically, that's it. You could represent a pixel with one bit. Okay? Then we're going to apply what's called an edge detection kernel. And this will basically pick up the edges of the blob. So if you see in the third image over, it's just an outline of the edge of the blob. Then we walk the image and find the start of an outline. Okay, so that's the red bars going across the top. And can you guys see the red one up there?
Yeah.
Mm-hmm.
Okay. From my angle, it looks really faded out, but I'm going to assume that's the screen. So when you find a blob, what you do is you wiggle along that edge, and you accumulate the pixels and update your bounding box. As you do that, you erase the image. That's how you keep track of where you've been. So when you get back to your starting pixel, you've gone all the way around the edge and back to the start. And you do this until all the blobs are found and you're at the end of the image. What you're left with is in memory, I'm showing them on the screen here, but in memory you've got a set of boxes that represent where the blobs were. Okay, everybody comfortable with how this algorithm works? Pretty straightforward? There's one part that's not, but we'll talk about that in a minute. Okay, this is how we're going to take a look at the complexity. Each one of the steps above is kind of the bold title on the left, and then there's some pseudocode. And I'm not going to get too deep into actually counting all these. It's more the concept. I spent a lot of time doing the math on the slides, and anybody who really wants to study that can study it in detail. Everybody cool with that? Okay. And you're going to learn a little bit about the image processing as we go through this. So, thresholding an image. This is pretty straightforward. For every pixel in the image, if the value is greater than some predetermined threshold, set it to 255. Otherwise, set it to 0. Okay? Just to show how we're going to count operations, that's 100 by 100 pixels. So we're going to loop 10,000 times. The loop itself is essentially a read, an increment, a write, a compare, and a test. And the test is, I'm counting that test as the jump. Okay, so that's there's 4 operations to implement a loop, roughly. That if statement is a read, compare, a test, and a write. So that's 4 operations. So at the bottom we've got 4 plus 4 operations times 10,000 loops is 80,000 operations. So it takes 80,000 operations with this outline to threshold the image. Okay? Everybody comfy? Okay. Now let's take a look at the edge detection kernel. So what these kernels are, if you do image processing, they're typically called convolution kernels. And they're a 3 by 3 matrix that you essentially stamp over the image. And at the center pixel of that image, you put the result of basically the, can't remember the name of the thing. Well, it's the formula at the bottom. Let's just go there. I can't remember the formal name right now. So you take the sum of each element times the one behind it, and then basically add them up. Okay? And that's so the value, actually let's start here. Start with the value of 0. For each kernel position, kx. For each kernel position, ky. So there's your 3 by 3. The value is the sum of the value of the pixel of that image times the value of the kernel for x and y. And you just add them up. And then you put that back in the center of the pixel. Everybody following kind of how that works? So you're doing 9 multiplications and 9 adds. Now, what you put in that kernel actually determines what it does. So different kernels will blur, sharpen. In this case, we're going to use an edge detection kernel. So what that 3 by 3 kernel is actually a set of 1 and -1 values. Okay? And when it happens, when you sweep that over the image, you get a difference right at the boundary where the edge is that turns out to be non-zero. If you're over the main part of the image, so if you're over, like, say, where it's all white, the sum of all the 1s and -1s cancel out. If you're over a 0, obviously it's still 0. But if you're right on that edge, you get a non-zero value for the target value. Okay. Next step. Walk the image and find the start of an outline. So for each pixel in the image, if the value is 255, then trace the outline. Going through the math, it turns out that's 70,000 operations. So tracing the blob outline, this is where the counting gets a little hairy, because this turns out to be dependent on the actual image that you're looking at. Okay? For each pixel in the border, so remember the red bands going across? You're just kind of walking right along the image, and then you find the start of a blob. Okay. What you want to do is look around that pixel. First you count that pixel, and then look around it and say, is anybody touching me? If they are, then you step to that pixel. And as you do that, you're looking at if x is less than your minimum x, then the minimum x equals the x. So this line right here is stepping. This line right here is counting and updating the bounding box. And then you've got a test. If you get back to your starting pixel, you're done. And you erase the image as you go. So that's all we're doing right there. That traces the blob outline. Okay, so if we add all this up, you end up with basically 832,276 operations for the image, and 57.25 operations for a border pixel. And that quarter comes from, let's see, so right here we're assuming a 25% trigger case for this if statement. And that's just a number I kind of picked out of the, it depends on how you actually walk, but it turns out that's about right. So you can estimate how you're walking around the border and what that's costing you. Okay, so what we have now is, we've gone through the algorithm, we know how many operations it takes for just a blank image, and we know how many operations it takes for some aspect of what's contained in the image. So, strengths of this algorithm. Pretty simple to implement. They teach this to students all the time. Pretty simple to understand. Everybody pretty comfy? Probably not experts on it, but it's conceptually pretty simple. And it's mostly dependent of image content. You'll find if you run this, the particular image doesn't matter a whole lot. If you look at the numbers, that's about right, because it's primarily dominated by this constant value of 832,000 operations. If it turns out you've got a completely white image, you still do 832,000 operations plus 57.25 for the outer border. If it's a completely blank image, it's 832,000. If it's something in between, it's somewhere in between. It doesn't vary a whole lot. Okay, weakness. This is pretty slow. We'll show that in a bit. It makes multiple passes over the image. So there was a thresholding pass, there was the walking pass, and you're altering the data. It actually has multiple working images. If you go to implement this, you find you copy from one image to the next when you're thresholding, so you end up with multiple copies in memory. It's not cache friendly. The matrix operation is crossing rows, so that's going to invalidate your caches. As you walk the border, you're hopping all over the place. That's invalidating your caches. You're moving between memory. You're dealing with a matrix. Not cache friendly at all. And the original image is destroyed. Okay, that's the traditional algorithm. Wanderer algorithm. So this was from an actual project. What we were doing was we were taking an imaging machine that imaged wood fiber inside of a water slurry. Okay. The original, and this was back in the Pentium 3 days, if anybody wants to kind of put a little spin on this of how much computing power we had. The original algorithm was something very similar to the traditional algorithm. The way that one worked is it would take a bunch of pictures in real time, store the images, and come back and analyze them later. The goal was do the image processing in real time, which meant about 10 images per second. So that's what we were doing. The imaging environment was completely controlled. This was inside of a metal enclosure. We had a video camera, water, lighting, all controlled. So we had complete control over what happened. The images themselves consisted of 50 to 200 very thin blobs. And by very thin, I mean almost just the border. They were maybe 2-3 pixels wide. No large blobs. We'll show this turns out to be pretty important. Everything was a thin image, or a thin object. The blobs are actually wood fiber. So like you would use, everybody know what MDF particle board or MDF board is? Yeah, this was actually the fibers they used to make MDF board. Oh, and the examples I've got only show a few blobs. So I'm not going to draw 200 of them. Okay, so here's the algorithm. The first one is threshold the image, just what we did before. Next one is find the start of a blob. Then we're going to explore that blob. And this is a little different. Does anybody notice we didn't do an edge detection on this? Okay, we've skipped the edge detection. We're going to explore the entire volume or the entire area of that blob. So the edge as well as the interior. Turns out because some of the blobs are curled, like that guy, you have to go do a double check when you do this because you'll walk part of it. And you do that till the end of the image is reached. Does anybody remember fill? So remember when Microsoft came out with Paint? Back in the old 286, 386, Windows 3.0 days? And you could draw a shape on the screen and you could say fill. And you could watch it kind of fill that thing. It would stop and it would kind of go around the corner and fill. That's how this actually looks when it runs. If you slowed it down and looked at it, that's effectively what's happening. Okay, for the complexity. Thresholding the image, it's exactly what we did before. Finding the start of the blob, exactly what we did before. The interesting part is when you find a blob and you start exploring it. So you found the top tip of a blob. What you end up doing is looking at the 8 pixels. So I found a blob here. I'm going to look at the 8 pixels all around that. And I'm going to find out which ones of those are set. Now the algorithm essentially looks at those 8 pixels and starts picking them off one by one and walking down that line. So what you see is, depending on the order you put the search in, it'll scan back and forth, it'll scan up and down, side to side. It has a definite search pattern to it. So the Explorer pointer, you start at the blob, you've got an offset. If the Explorer pointer is an untouched pixel, then jump down here and accumulate the pixel. This is the same test case we did before, that updates the bounding box. Turns out you count the pixel in this case, and then go back. And then you move your Explorer. Excuse me, you update it with a constant tag, sorry. So I was using bit setting in here to determine which pixels around my target I've actually explored. So I'm just setting a bit flag on each pixel as I explore it. Okay, let's go down here. Continuing to explore, once you've looked around the pixel that you're in, you move to the next pixel. So you explore right, down, down, right, left, right, basically the 4 directions around that pixel. And if that pixel that you're looking at is greater than a completed pixel, meaning you still need to look at it, then you move your offset and your Explorer and repeat the above process. So you're just walking through this pixel, setting bits and counting them up. Once you're done, you need to take to double check, you need to take the bounding box that you found, expand it a little bit, and see if there's anything else in that expanded area. Okay? it turns out if you get into a corner and you don't do that, you'll leave part of the blob undetected, and you'll count as a separate blob. Okay, complexity. So thresholding the image, 80,000, just what we had before. Finding the start of a blob, same as traditional, 70,000. Exploring the blobs. So now we're looking at how many blobs are, or how many pixels are in the blob is what this really becomes dependent on. So it turns out you got about 55.5 operations per blob pixel, and the double check ends up to be about 48 operations per blob pixel. So you add it all up, you get 150,000 operations for an image, and 103.5 operations for a blob pixel. Okay, so how does this compare to the last one? So, slide's a little strange. Traditional's on the top, Wanderer's on the bottom. Operations per pixel. For a blank image, we went from 800,000-ish operations down to 150,000. Okay? Where did most of that come from? The convolution, that matrix operation. Turns out that's pretty darn heavy. But look at ops per feature. So this is actually fairly interesting. 57.25 blobs for a border pixel, or 103.5 per area pixel. It's kind of comparing apples and oranges, right? In one case I'm just looking at the border, the other case I'm looking at the area. Why does this actually come out ahead? Well, the performance of this algorithm greatly depends on what's in the image. So if you've got an empty image, Wanderer is very, very fast. Okay? Basically, for an empty image, that's the comparison. It's almost, what, about 6 times as fast-ish. If you have large blobs, it gets very bad. Matter of fact, if you give this thing a large blob, it can take a second or more to pick it out. An all-white image, its worst nightmare. Remember, this application had long, thin blobs, mostly only a couple of pixels wide in width. Therefore, the blob area approximated the border pixels in practice. So even though we've got more complexity and cost for an area pixel than for a border pixel, those two end up pretty similar, and it's really about a factor of 2. Turns out that this metric dominates, and that mostly cancels out in practice. Not completely, but mostly. So strengths of this one. Turns out this is 15 to 30 times faster for the target images than the commercial library was. There's only a single copy of the image. Everything's happening in place. That saves a whole bunch more time. The image is altered, but it's still available. Basically, it turns to a mid-level gray. Weakness. This thing's actually pretty complex to implement. Figuring out the wandering directions and so forth, not simple. It's highly dependent on image content. If you give this something, an image outside of its boundary, you're kind of done. There's multiple passes over the image, and it's not cache friendly. Okay. Ready for the last one? You guys still awake? Okay. This one was from another real-world application. I can't give much detail on what this really was, but the objective was to track 5 to 10 small round objects per frame. The goal of this was to run on very, very small processors, like microcontrollers. So small, you don't even have a frame buffer to hold the whole image. So you notice everything before, we had 1 or 2 copies of the entire image in memory at a time. This particular algorithm only needs to hold the current pixel and some accounting data. The image content was mostly controlled. It was not in a box, it was out in an open environment. But the object that we're tracking was a narrowband infrared emitter, and the camera was equipped with a narrowband infrared filter. So we were using, basically we were using physics to simplify the algorithm. Those two filters matched, so essentially what you got was a black and white image that showed just the dots, and as long as you didn't have sunlight running around, everything was fine. Okay, you can see from the number of boxes, this is already a pretty simple, or a simpler image. For each pixel in the image, threshold the pixel and detect segment starts and ends. So what's a segment in this case? You guys see the little yellow bar up on top of that pixel? Essentially what you're doing is walking the image and noticing when you get the start of a line and the end of the line. That's what I'm going to call a segment. Okay? When you find the start of a line, you start accumulating a segment. When you find the end of that line, you've got a segment. Once you've got a segment, walk an array or a linked list. This example is going to use an array because it's simple. Walk an array where you're accumulating these segments and figure out which one it connects to. Okay, and you can do that by comparing the start and end of the segment. Yeah?
Well, if you don't have any memory, how are you going to, what if you have a lot of segments?
Yeah. So one of the criteria of this one is you knew you were only going to get about 10 of these things. Now, it turns out you're not keeping the segments. What you end up keeping in memory, you only have to keep for your accounting, you only have to keep the bottom edge. So you keep the bounding box and the bottom edge for each object you're tracking. So it ends up being, I'm trying to remember exactly off the top of my head. 4 inch, 8 inch for the bounding box, and 4 inch for the lowest most segment in the simplest case. So what? 8, 12. It's under 300 bytes of memory, and you need to keep track of everything. So it actually ends up tiny. Now, keep in mind that breaks down if you get tons of stuff in there. But it's however it works out, it's much less than holding the entire image. Okay, when a segment's complete, you add it to the connecting blob structure. All right, this one's a completely different algorithm. You have to set up a bunch of setup variables. Are you forming a vector? Probably actually should say forming a segment. False. Your pixel scanner sets the image start. Your current x and current y are 0. This next part is a little subroutine we're going to use. Insert a blob line or a blob segment. Basically, this looks, it walks the array, assuming 10 blobs at all times, and just says, is the end, I'm just going to do it graphically. This is a segment, and this is the tail end of the stuff I'm accumulating. Basically, if they're like that, they're not touching. They're that, then this segment belongs to the blob, still belongs to the blob, still belongs to the blob. So what you ended up doing is the comparisons of the start and end of each of your segments against the start and end of each of the blobs that you're holding in memory. And just saying, do they overlap? That's all you're looking for. So that's what all this is doing, just walking those comparisons. Then you walk the image. Pretty much the same thing we did before, except notice the first line. If the value of the pixel scanner is greater than the threshold, I'm still thresholding. Still have to do that, but I'm doing it pixel by pixel on the fly this time. So I don't have to write it back to memory. I can just hold it in a register. Or as I've done this, it's ready for just ready to be consumed. Then you basically have two states. Are you forming a vector or not forming a vector? Or a segment? And you just basically do the steps as appropriate to either add to your current segment or store the segment that you've got. And then, let's see. Oh, this last little part right here is a special case for walking off the end of the image. So if you've got a line segment that touches the far end of the image, you have to say, okay, I'm done, because I've hit the end of the image. Okay, going through all that math, you end up with 40,000 operations, 40,100 operations per image, and 155 operations per blob line. So again, we're comparing now apples, oranges, and bananas. Let's see. I'm going to do this slide first. Okay, so this is the how the math all works out. We've got all three algorithms in place. So notice we went from 832,000 operations for a blank image down to about 40,000 operations. At the same time, our ops per feature is about tripled. The ops per image consistently goes down. So if you consider an empty image, this one's going to be way faster than the other two. But if you get stuff in there, then it starts slowing down a little bit. Now, we only had 10 objects. The other thing to consider is 155 operations per blob line. Let's compare that to a blob pixel. In this particular algorithm or application, a line tended to have about 10 pixels in it on average. Okay, so for the average case, we could divide that by 10 and say 15 per blob pixel. Okay, so kind of turn the banana into an orange. Okay, let's go through the strengths and weaknesses. This algorithm is extremely fast. There's no benchmark. We ran it on a Raspberry Pi, or no, I take that back. It wasn't a Raspberry Pi, it was a Atom processor. It was the smallest thing we've run it on so far. And it didn't even know it was running something. Basically, on a little Atom processor, this algorithm was lightweight enough that the image transfer from the camera pretty much dominated. So the image processing had very, very little overhead. There's only a single pass through the image, and you only need to have 1 pixel of the image at any time. If you can buffer the entire image, it's untouched. The original image is not altered, so you can carry out whatever other operation you want on it. This is actually pretty simple to implement, and it's about as cache-friendly as you're going to get. You read a pixel, you do all your operations on it, you never write that back, and you're always reading the pixels in row order. So short of having to write the little housekeeping notes off to the side, it's about as cache-friendly as you're going to get. The performance suffers with a large number of blobs. You pointed this out. If you turn out you've got 1,000 blobs in here, you end up searching about 1,000 of these entries as you go, and figuring out where this matches up with what. It turns out that we actually tried that. It's not super bad. You do get a drop in performance, but you still get gains from the overall image, or from the overall algorithm. There's one step in here that I left out, and we were able to do it in this case because we had round images. If you had a curly image, like in the first one, depending on which way it curled, so if you're doing this, imagine an image that starts out this way and then meets at the bottom. You have to deal with joining these two partial segments into one. Let's say you had one that looks like an N. So it starts out and then the two sides go down. You have to deal with that as well. I actually have some stuff in there to deal with that, but you don't need it for this particular application. It turns out it's very complicated to talk about because there's like, I believe there were 8 or 9 cases you have to deal with, depending on the morphology of the blob. It turns out they're not that hard to put back together. Although bet you're going to pick this up. It is an n-squared problem.
Well, back in the old days, there was a related problem. It was the AI for computer games.
Uh-huh.
And a lot of the AIs would only work with round objects.
Oh, interesting.
Anything concave and the algorithms would all fail.
Yeah. Probably a very similar problem to what I saw here. Okay, so in summary, matching the algorithm to the expected use case and input can greatly improve performance. So if we go back to that guy right there, yeah, what do we got? On ops per image, it's about 20 to 1. If we take this normalized of 15.5 per line, it's about 4 to 1 per feature. So if you let me bend the stats a little bit to kind of compare apples and oranges, it's better across the board. The metrics actually prove that out when you run it. These gains are completely additive to other optimization techniques. So using a fancy compiler that has good optimization, writing good efficient code, all that stuff, these just add right to it. One thing that's important to consider when you're trying to figure out how to build an algorithm for a particular problem, this single pass algorithm actually took me several weeks, and by coincidence, a couple trips to the airport because I was wandering around with nothing better to do but wait for somebody, to come up with how to do this algorithm. There is not a way I'm aware of, so like the Wanderer algorithm, you could somewhat derive from the traditional. So if I look at the traditional algorithm and I say, how can I make this better? Okay, getting rid of that matrix convolution multiply. Obvious step. Okay, that's really what was done there. Single pass, you really can't do that. You have to start with a whole different way of thinking. And that actually turns out to be pretty important if you really want to get significant gains for a particular application. You have to not necessarily look at what have people done in the past and what are the general algorithms that people have applied. You have to get your mind out of that mode and go to a mode of, this is the specific problem I need to solve. This is the only problem I need to solve, but I need to do it as fast as possible. And then be a little creative.
Since it's a not obvious algorithm and it took you a while to come up with it, are you going to write a paper about it or something? It seems like it would be of general interest.
I could, if it's that interesting. We were initially thinking about patenting it when I wrote it. And it was kind of like, well, that's really not a good patent. Yeah, I figured I'd get that response here. Okay, this is not patented. The implementation itself is still on a live project. So I don't want to just absolutely publish it yet, but I did get permission to do this presentation on it and give the general idea. It turns out computing power is getting fast enough now. This was originally done back in 2011, I think. And small processors were still a little more constrained than they are today. Today it's pretty easy to get a 300 or 400 megahertz 32-bit ARM processor for under $5. That was not the case back then. You got about, if you were lucky, 100 megahertz. And the performance wasn't all that great. Yeah.
Yeah, I was curious of the reason for constraining yourself to the microcontrollers.
Yeah, so the primary reason for constraining it was cost. So I mentioned we've run this on an Atom processor so far. And that was in one of the little ASUS ultra lightweight notebook thingies. The eventual goal of this is to place it into a device with the functionality essentially of a webcam for about the price of a webcam. So a total BOM cost of $5 to $10.
Well, can you tell us what this thing was that you were building? Okay.
I'd have to kill you.
Yeah, all right.
I got enough permission to tell you all this stuff. I can't give you quite the fun. But let me tell you this though, because we were talking about where the inspiration for this thing come from. Turns out I do both hardware and software. Anybody ever taken apart a webcam and looked at the little processor inside? It is absurdly simple. Most people think a webcam works like a regular video camera. So like, we're recording this in the back. There's a video camera there. It's got an imaging chip on it. That imaging chip stuffs some stuff out to a memory buffer. It gets compressed and eventually stuffed onto an SD card. Webcams don't work that way. Webcams have a imaging chip on them, similar to a chip you'd find in a video camera. A little smaller, a little simpler. They output the pixel information in a serial fashion. So it's a serial output. The chip is simply responsible for grabbing that several bytes of that serial block, or that serial stream, packaging it up into a USB packet, and shoving it across the bus.
What's the frame rate of those webcams by doing 1 pixel at a time?
It actually ends up limited by two things. It's dependent on the USB bandwidth, which for 2.0 will get you, it'll get you a color HD image at 30 frames a second just fine. And it's limited by the clock rate of the imaging chip. So essentially the imaging chip runs at a given resolution and a given frame rate by design. That's the product of the length width times the frame rate times the depth, count it 3. Well, it's not actually even 3 because it's a bare pattern typically, so ignore that for the moment. It makes the conversation a lot messier. Just assume 3 bytes per color pixel. It's wrong, but let's just assume that. Multiply those together, and you end up with a clock rate, depending on your resolution, in the hundreds of megahertz, which is still doable on a chip. So they can stream out a 30 frame per second image at full resolution, serially, not a problem. Almost all imaging chips, including the fancy ones in fairly high-end webcams, stream out serially.
So we still haven't gotten away from raster technology.
Well, there's a thing called a global shutter camera that does.
Okay.
And it actually exposes an image and then direct copies it to a memory buffer in the back. Okay, so instead of this scan line down, which is a raster scan, it does a snap and then a copy. And then it scans out of that. Now, the fancier chips actually come out on several lanes. So if you get to the fancier chips, there's camera serial interface. You'll hear CSI. It's what's called a MIPI protocol, and I'm starting to talk hardware protocols here, so I'm probably going to lose everybody. But that is divided into lanes. Each lane contains a bit, and commonly you'll get 4 lanes. So instead of shifting it out 1 byte at a time, you're shifting it out, 3 to 4 bytes at a time. Or those can operate at very high speed in some cases, and they can run out gigahertz speeds off of that bus on a single bit.
So is the processor on the webcam or in the device that's connected?
There's 2 of them. So in the really fancy high-speed imagers, and we're talking machine vision cameras here, and well, actually, the camera on your cell phone would work like this. There's a very small processor on the camera chip itself, and it can, in addition to just scanning out, it can perform various corrections on the image. White level corrections, color corrections, clipping. I've seen some that can do rotations. So there's a processor there that's in the image path, and then it goes to this MIPI bus, which is a fairly flexible protocol. Goes to a MIPI receiver on the SoC of the processor in the system, And then that's an ARM processor. So it's almost like a serialized DMA operation coming across that.
I would think if the bandwidth is a problem, you could have a processor actually compress it in the camera. And
Yeah.
then,
Well, and actually, matter of fact, some of them do.
okay.
Yeah. Depending on the camera, some cameras will spit JPEG straight out of them. I tend not to run into that a lot in the machine vision world for one major reason. JPEG's lossy. So if you get to get the most bandwidth gain out of that, you have to use the lossiest compression. Lossy compression and machine vision algorithms tend not to like each other. You can make it work, but and I've done things like that. When you pull off of a webcam, it typically comes across as a JPEG image as well. And again, it's in the display chip. Okay, final statement is the typical statement that you have to give with any performance talk. Always measure actual performance. Measure, measure, measure. Optimize after that. And well, that's me and my cat. Anybody have any questions? Okay, yep.
Can your vision detect your cat? The famous vision problem is detecting the cat. So.
Haven't tried yet. A lot of the vision problems I end up with a camera inside of an imaging box, which means I'd have to put the cat in a box, and then I'd end up with Schrodinger's cat.
Well, it's hard to tell if it's one or two cats, too.
Yeah. It's also hard to tell if it's dead or alive. But wait, you've got a camera in there, so isn't that an observer?
Yes,
Well,
yes.
in your case.
It is quantized, yes.
Yeah. So it's quantized, digitized, and then probably pissed off because the cat's in the box.
Right.
This cat does not like to be in her carrier, I'll put it that way. Okay, other questions?
I think it'd be interesting if you could talk a little bit about some of the control mechanisms that you do to make better images.
Oh, sure.
So you did,
Just general machine vision stuff?
Yeah, you said
Yeah.
the last one was sort of infrared with a filter. The other one you said was lighting and some kind of liquid
Sure.
container.
So this is actually
First, I guess what's some of the goal there? Like it seems like the goal is to sort of make the environment do the threshold filtering for you, right?
that's actually a lot of it. Yeah. Let me generalize that. So the goal is to make your. Let me say it this way. The goal is to make the physics of your imaging setup do as much of your imaging work for you as possible. Okay? You get that for free. So essentially, what this entails, and this varies, well, let's back up for a second and talk just a traditional industrial machine vision environment. Okay? So a couple reasons for that. One, you're in a machine. You're doing the same thing every day. You get to control basically everything. That's very different than a self-driving car that gets no control over anything these days. Okay? But in a traditional industrial machine vision application, you control the lighting, you control the flow rates, you control the camera, you control the focusing, you control the lens. Okay? You control any filters on all of that. So depending on what you want to look at, the goal is to arrange that to do as much work for you as it possibly can. The typical workload is segmenting foreground and background. What do I care about? What don't I care about? Okay? So in the fiber sample, when we were imaging wood fibers, they were being carried in water. The way that was set up is you had a camera on top, you had a very nicely designed lighting array. Okay? The goal of that lighting array was to illuminate the target image from all angles as evenly as possible. Now, we can do that a lot better today than we could back then. because we have LEDs. We were originally using 2 halogen lights. Does not provide very even illumination. So what you do is you just basically hold the lights back and flood the area with a ton of light, and take the little spot in the middle that was even. Okay, with LEDs you can point them around more and you can pick different cones and so forth. So the problem you end up in that case is if you do not have even illumination. You notice I was just thresholding on one value. Okay? If you look at an illumination curve, typically across a camera, there's several effects that give you this dome shape. Okay? The image is dimmer at the edges than it is in the center. There's several reasons for that. There's lighting effects from your illumination. There's what's called vignetting, which is a function of the lens. Turns out, rays in the center have more direction that they can come in and pass than rays at the edge. They're cut off. It's an edge effect, essentially. The actual optics of the lens gets into a little bit of that. So what you want to do is arrange all of that with your focal lengths and the area that you're imaging with the camera to minimize as much of that as possible. Another trick you can do with the lens is you typically match a lens to the size of imager that you're looking at. Okay? One trick you can do is overshoot the lens. So basically the lens thinks it's looking at a bigger image, or a bigger imager, and focusing on a bigger imager than you really are. What that does is it gives you just the center of that lens, where vignetting effects and lighting effects are minimized. That means I can use a simple thresholding algorithm. I don't have to do what's called a spatial threshold, or a zoned, or adaptive, or one of about 100 other different thresholding algorithms that are way more complicated and to deal with these other effects. The other thing that we did is in the fiber case, you had a camera, you had a lighting array, we had a plastic block that was essentially where the water and the fiber was flowing. The back of that block, behind it, was built as a light trap. So essentially what we had is light went down, light hit a fiber, only that light came back to the camera. Again, that means I don't have to deal with background images, shadows, glare, all these other real-world things. Like I noticed you're wearing glasses like I am. Look at the edge of your lens. Well, actually you've got full frame, so you may not be able to see it. But if you look at the edge of your lens, there's a bright ring right along it, as the lens catches light coming in from various directions and just happens to bend it to where you can see the edge of the lens. All these things, end up being a factor. Let's just take another hypothetical example. Another thing they do, manufacturing any type of bottle or pop can. Have you ever seen how a pop can's manufactured? Starts out as a metal disc, about yay big around, okay, of aluminum. First thing they do is smash it. Next thing they do is extrude it. So they take that disc and they take a pinion and they just basically shove it like that. So essentially they stretch the aluminum to form the can. Got an idea what that might do in some cases? Occasionally it leaves holes in your can. Okay, if the metal's not completely uniform, it won't deform smoothly. So anytime you see any type of stamped can, they'll always have a test at the end to see if there's holes in it. What's the easiest way to test to see if there's a hole in a can?
Liquid in it?
Nope, even faster than that.
Put pressure in it.
Put the light inside and see if the light goes up.
You got it.
There you go.
Put a light bulb inside the can, put the whole can inside of a dark environment and see if there's any light. That's exactly what they do. Guess what? That doesn't even take a video camera. You can do that with a photo cell or two if you I think I've actually seen it done the other way around, where they put the light on the outside of the can, they put the detector inside, because it works better. You can do it either way. But that's a perfect example of how do you arrange the physics of what you're doing to eliminate as much processing as you can. So in that case, you could do that with a simple analog circuit.
So do, like another question, do things just get more complicated? Like if you have potentially multi-lens setups, then you basically have multiple frames, and then
Yep.
potentially you can convolute not just over the face of an image, but through the depth
Yeah.
of your 3 or 4 images you're
Yeah,
working with. And
and depending on what you're doing, the general rule is the more complicated your setup, the more complicated your software has to be to deal with it. If things are moving, you have to go to what's called, well, if things are moving and you care, you either have to go to ultra high-speed cameras to stop motion, or you have to go with the global shutter. So that, you remember I was talking about, instead of scanning it out line by line, you snap the whole thing and then transfer it to basically a bank of memory in the back and then read off that memory. One of the things you're doing in industrial machine vision a lot is measuring things. So in the case of the wood fibers, we were actually measuring the size and shape of the fibers. If the fiber is moving when you image it, it will blur and it will stretch in the direction of motion. Matter of fact, you get some of that anyway, even with a global shutter. So you have to control the flow rates and things like that. If you cannot control the flow rate, then you have to essentially warp or morph your image or your resulting values to compensate for the motion. So yeah, every little thing that you can't control in the environment, you have to control for somehow in the software. Okay, other questions? Oh, we're at 8:15, so let's call it a wrap. Thank you, everybody. All right. Stop this guy.
What time does the meeting start?
7.
Are you going to have our pizza sponsors?
Oh, did you guys want to say anything for?
Well, yeah, sure.